Okay, let's talk about GPS. If we put two GPS recording stations on either side of a fault and let them record constantly, they can really get down to sub-centimeter accuracy of location. Just leave them recording and the error gets minimized out, and eventually you really can pinpoint down the location of this area. So in this case, this one station on the left-hand side of our fault, which is there in the middle of the screen on black, and we're going to consider the right-hand side of the fault pinned down. We're just going to move the left-hand side, in this case, up. The location of the satellite dish or the GPS recording station on the right-hand side stays exactly the same, and the one on the left-hand side moves up about 1 second, which is about 30 meters during a certain amount of time, between time 1 and time 2. We have that much elastic strain accumulated on the fault. We can measure these and we can tell exactly what the displacement would be when the fault ruptures. So now we understand that the displacement of this fault would have been about 30 meters during this one particular imagined earthquake. So again, GPS units on either side of the fault can measure how much the plates on either side of the fault have been moving, but the fault itself hasn't moved. So you have that strain that's accumulating on the fault. And eventually, when the strength of the fault is compromised, the stress is just too much and the fault actually ruptures, this can tell us exactly how much displacement there will be at a given time on this event. And then we can go back and figure out, using different ways of geology, how long that fault was, how deep it is, and get an idea of moment, which we talked about last time, release on this earthquake. Okay, synthetic aperture radar interferometry. This is a satellite technique, which is quite complex, takes a lot of math, and I want to explain it at a very simple level. To get into a little bit more is a little bit beyond the scope of this class. However, it was this method that was able to prove that the earthquake that happened in Haiti did not occur on the Enriquillo Fault as was originally suspected. Okay, here's how the method works. If we have a satellite that is flying over the area and it's very well located as far as elevation above the planet, it's in geostationary orbit. I'm not sure if it's actually a geostationary orbit, but it's at the exact same elevation all the time. They can really track its location precisely. This satellite sends out signals, microwave in this case, signals down to the ground, and they bounce back off, giving a very precise measure of elevation of the land. If there's an earthquake and the land is deformed, in this case this is a thrust fault that's pushed the land to the left up and land to the right went down a little bit. We come back, we measure again from the exact same place the elevation of the land, and then we compare those two records. We'll have a slight shift in phase of this wave. So you can see how the waves, if there had been no movement, the waves would have come back and been exactly in phase. You would only see one sine wave in this case existing. But since the ground came up, the phase of the wave has actually shifted. So you can see an offset in the wave. Let's look at this a little bit more carefully. This phase shift is represents about the amount of vertical displacement. So if we have a wavelength, in this case, of about 3 centimeters, you can see that a phase shift is on the order of, I don't know, I'm guessing about 7 centimeters in the example I gave. I put an N after that because sometimes it's hard to see exactly how much displacement there is, because if the phase is shifted, when you come back around at different intervals, you'll see that that phase shift will add up at different places at different times. What you end up getting is something that looks like this. What this shows is that in the area focused right around the elbow of this little bay, there is actually a fair bit of uplift. And uplift is something that should not happen on a transform fault. The Enriquillo Fault is mostly a transform fault. However, if you remember that image, the plate motion wasn't exactly parallel to the fault, but it was actually coming at a little bit of an angle. What happens in a lot of faults is there's what they call strain partitioning, where the lateral or transform motion of the fault is taken up mostly on one fault, but you can have a series of faults that actually take up the transpressional or the non-parallel component of that plate vector on, in this case, reverse faults. What Eric Calais showed using this interferometric data is that it was, instead of it being a transform fault, it was actually a reverse fault that caused this earthquake. And what that means is that that transpressional strain, the strain that's occurring on the Enriquillo Fault, has not been released. So that fault is still accumulating strain since 1751 when that last earthquake hit. That is very dangerous for Port-au-Prince, which is up there in the northeastern corner. Okay, so if we summarize this quickly, we can see the main Enriquillo fault there running through the south part of Haiti in red, but there's all these other faults, these little yellow faults and these purple faults that are coming off. Which fault exactly this occurred on? Probably one that's unmapped. It might be that little yellow fault by the west there. It does matter, of course, because the Enriquillo fault could still be accumulating strain. As you can see from this image, it goes right through the southern part of Port-au-Prince. As you consider exactly what methods you want to use for determining what the seismic risk is for a given area, you want to know how big the earthquake is likely to be. So this is one of the methods you might consider using. Thanks, and we'll see you in class on Tuesday.